Okay, so now we're continuing on with improper integrals and looking at functions with some discontinuities. So if we have integrals of functions that become infinite at a point within the interval of integration, then what do? So for example, f of x is a positive continuous function from a but not including a to b, then really we're finding the limit of that integral as a gets as the function gets close to a from the right. Then, so in this case, in terms of a limit, we'll call it c, in this, call it t, whatever you want, but that's going to go approach a from the right, so the a plus, all the way up to b. If it was sort of on the right-hand side of the value a, going to b, where there's a discontinuity of b, then we're approaching b from the left, and then it could be a variety, right? So a union. So you just keep adding. There could be quite a few points of discontinuity, okay, or asymptotes. So taking a look at this one, look and see what your function is defined for. So this 1 over root x is defined for all values of x except 0. So when this says evaluate this interval from 0 to 1, we can't actually put 0 in there. So really what we want to do here is take the limit, and then again you can use a or t, whatever you want. I'm going to keep using t. So from 0, t approaches 0 from the right, because this is starting at 0 going to 1. So this will then be t here to 1 over root x dx. Okay. So now, integrating that, that's going to be, so that's x to the negative 1/2. So add 1 is x to the positive 1/2 over 1/2, which ends up being 2 root x, t to 1. And then that's going to be the limit. T approaches 0 from the right. 2 root 1 minus 2 root t. And so now we can take that limit. As t approaches 0 from the right, that's going to be 2 root 0, which is 0. And this is 2 times 1, which is 2. Okay. So really, again, it's kind of a matter of notation, putting it in limit form. Take a look here. So you do want to, though, make sure you check for those asymptotes or points of discontinuity, because it could change it. If you sort of negate that from your solution, your area may not be correct, or your integral. So in this case, x, so this factors to x plus 1, x minus 1. So x cannot equal plus or minus 1. So we have to set this up into 2 parts. The negative 1 isn't going to come into play here, because take a look at your indices from 0 to 3. So we don't even care about that negative 1. So we're going to go from limit. We can start at 0, so this will be, so we'll go from t approaching 1 from the left, and so that's going to be from 0 to t, 2x cubed roots, and then plus limit. Now we're going from the right of 1, so we want, in this case, t approaching 1 from the right, going from t to 3. Okay, so same interval, different boundaries. in order to evaluate this interval, I think I'm going to let's let u equal x squared minus 1. So du would be 2x dx. And then that means, so if I do kind of this work on the left here, that's going to be du over cubed root of u squared. So that's really u to the negative 2/3. Okay? So this is equal to u to the negative 2/3 du. So integrating that, that's u to the, add 1, so that's 1/3. So that's 3 cubed root of u, which is x squared minus 1. So, this is limit t approaches 1 from the left of 3 cubed root of x squared minus 1 from 0 to t, plus limit t approaches 1 from the right of 3 cubed root x squared minus 1 from t to 3. Can't combine it into 1. I use t's, but they're separate, so that's okay. They're separate terms, but you can't combine it to 1 because t is approaching 1 from different directions. So maybe you might want to use t here and b in the second one, or something like that. Space. So we've done this, figured that out. I'm just going to erase that. Right. So this is going to approach negative 1. So this is 1 from the right. That's right, 1 from the left. Still going to be 1 squared. It's a cubed root, so even if it was negative, it's okay, but this is going to approach 0 in here. Okay, so this approaches 0, the first term, as t approaches 1 from the left. The radicand approaches 0. This is going to be minus 3 times negative 1 times negative 1. Plus, then 3 times cubed root of 8 is 2, minus this approaches 0. So that's going to be 3 plus 6 equals 9. Okay? Right, so first thing always to look for are non-permissible values. Take a look, are any of them within the indices in the integral? Then split it up, because obviously it's undefined at those, and go from there. Okay, show that the improper integral diverges. All right, so we're telling you that it diverges, so let's see what happens. It's going from 1 to infinity, so this is going to be equal to the limit as t goes to infinity from 1 to t. I'm just going to show it as 1 over x dx. So we know that the graph of 1 over x looks like this. So you kind of think, okay, well 1 over x, it's approaching the x-axis, right? So each y value is getting smaller. But we're looking for the area underneath. Does it approach a particular value? Obviously it doesn't if it diverges. So let's see what happens here. So we're going limit, t approaches infinity. That's going to be ln of x from 1 to t. So limit ln of t minus ln of 1. Well, ln of 1 is 0. So this is where you see limit t approaches infinity of ln of t. Well, as t gets bigger, ln gets bigger. Not hugely, but it does. So this goes to infinity, right? So it does not diverge. So we can never get the area underneath 1 over x for an infinite area. So just be aware of that, because you kind of think about, oh yeah, if 1 over x is approaching 0, but the area underneath not approaching the number. Okay. Then question here, does the integral from 1 to infinity of e to the negative x squared dx converge? Since the antiderivative of e to the negative x squared is difficult, if not impossible to determine at this level, we need to compare it to another integral. Okay, so this is called the comparison test. So if f and g are continuous on the same interval, and they're both positive functions, so greater than 0, and f is less than g for all x values greater than or equal to a, so in this interval here, then f will converge if g converges. Okay, so it's kind of like the sandwich theorem, that kind of thinking, right? So if we know what happens to g of x, and f of x is between 0 and g of x, then f of x will converge as well. Then, and this on your notes, hopefully I fixed it. I think it said if f of x diverges, I think it said f of x diverges if g of x diverges. So we can't tell from that. This fix it if it's not fixed. So g of x will diverge, this will diverge if this does. Because if this is bigger and something smaller already diverges, then the bigger one has to diverge as well. Okay, so just make sure it's correct on your note sheet. So determine the convergence of this function here. So we want to do this by comparing to something still that's sort of equivalent. So if it's an exponential e to the negative something, see if you can compare it to a function that's similar to that. So I'm going to compare it to 1 to infinity of e to the negative x dx. Okay, now think about this. So e to the negative x squared smaller than e to the negative x, right? And this is the one we want to find out if it converges. So if we can figure out if e to the negative x converges, if it does, then e to the negative x squared will converge. So let's do that. So this is going to be equal to the limit as t goes to infinity of 1 to t of e to the negative x dx. So integral of that will be negative e to the negative x. Fix that up. Okay, and then, so, I'm going to show this. This is negative 1 over e to the t. This is going to be plus 1 over e. Okay, so as t goes to infinity, this will get really big, so that will go to 0. So this is going to equal 1 over e. That is, it converges to a value, so that means you can find the area underneath that curve approaching infinity. And because of that, we know that therefore since e to the negative x squared is less than e to the negative x, and e to the negative x converges, then integral of e to the negative x squared converges. Alright, so you want to find something that's very similar. Don't choose an entirely different function if you don't really know if it's always less than, or something sort of too much bigger. But if it's equivalent, so in this case exponentials with a negative exponent with a variable in it, then you are pretty much guaranteed that it's going to converge. Okay, so we've talked about volumes of revolution in calculus. This is just an infinite volume of revolution because now we're going from 0 to infinity. This graph doesn't actually ever cross the x-axis. So the volume, remember, is going to be pi times the integral of the function squared. So that's x e to the negative x squared dx. In this case, from 0 to infinity. So we want to take the limit, so you can factor out the pi, and then limit t goes to infinity, 0 to t, what's that, x squared e to the negative 2x dx. Alright, we're going to have to use integration by parts. So u equals x squared du equals 2x dx. dv equals e to the negative 2x dx. So v equals negative 1/2 e to the negative 2x dx. Okay, so then so this is going to be uv minus the integral of v du. So the 2's will divide out. It's a minus, so that will be a plus. X e to the negative 2x dx. This is from 0 to t. And this will end up being from 0 to t. Then we have to do it again. So then we'll call it u2 equals x. So du2 equals dx. And then dv2 equals e to the negative 2x dx. And then v2 equals 1/2 e to the negative 2x. Lots of work on this one. I'm just going to leave this before I start substituting in. Okay, then it's going to be uv, actually minus half x e to the negative 2x, minus, so uv minus the integral of v du, is to plus 1/2 out front, e to the negative 2x dx. Alright. Let's start substituting it here. Zeros go away. The side bracket there too, right? And then what is that? So that's going to be negative 1/4 e negative 2t minus e to the negative 2 times 0. Kind of doing that all at once. Okay. So let's group the factor of e. Actually, I'm going to show this a little bit. So that's going to be plus 1/4 e. Not 1/4 e, sorry, it's 1/4. Because e to the 0 is 1. Got squared there. It's e squared. It's going to be, so the factor, actually I'll factor out a negative 1/2 at the beginning as well. So negative 1/2 e to the negative 2t, I'm going to factor out. So I'm left with t squared plus t plus 2 plus 1/2 and look at that. I changed that to infinity. Okay, to 0, it's supposed to be infinity. Okay, so now what we really have here is a negative t squared plus t plus 1/2 over 2e to the 2t plus 1/4. And what happens here, as t goes to infinity, we want to know which grows faster here. If you think about it that way, or can't really compare it exactly, but we can take L'Hopital's rule, right? So we want to take the limit of this. We can use L'Hopital's. So that's going to be negative 2t plus 1 or e to the 2t. And it's still plus 1/4. Still infinity over infinity. L'Hopital's again. So this is going to be, we can factor, so this is going to be pi. This here goes to infinity. So that's going to approach 0. And so really we have 1/4 left. So that's going to approach pi over 4. a lot of work. Probably not going to give you all that on a test, but it is really good practice, and I just kind of messed up that. Give me a sec here. There we go. All right, so we ended off with a long one. Did make a couple mistakes, but I corrected them in there. Really good practice on integration, but really the theme of this is volume of a solid that is a function that doesn't ever touch the x-axis. Then you're using an improper integral, going from 0 to infinity and finding the limit from 0 to t, where t approaches infinity. All right, there you go.